It's a pleasure to be here again this year. Lots and lots of things have happened since we met in Huntsville last year, including our test flights, some major changes in Washington, and various agency support. So this afternoon, I'd like to talk to an update. Start out with kind of an overview for some of you who may not be familiar with our particular concept and objectives. Talk to what we're accomplishing have accomplished on the Delta Clipper experimental to date, and then a little bit about what's next in our new partnership with NASA. The Delta Clipper SSTO, as you've already heard this afternoon, falls in the category of looking for the low-cost, reliable transportation to and from space, which really needs to be the starting point of space expansion. It stands to reason that if you can't get there, you can't expand. And for most all of us in this room, we can't get there because it costs too much, and we probably have to wait too long even if we could afford it. So our whole thrust of the program has been dedicated to getting affordable space, getting it into a routine nature, and being kind to our environment as we do it. The thrust we've been following has been for a vertical takeoff and a vertical landing system that draws on the capabilities that have been demonstrated with work that's been already accomplished for the Air Force in our ballistic missile world for precision flyback systems, which, although at first glance it may not look, but it is a very highly effective hypersonic lifting body, which we also use to give us cross range and precision direction for landing. It also is implied from the artist's conception is the very streamlined nature of the whole ground system and operations as well, because that's really what is key to the whole system is the low-cost operations. And so from the beginning, as you've heard from others, the system has been designed first for operability and supportability, and then next to provide the mission performances that are needed. This is drawn heavily on both our commercial and military aircraft side to get it into very routine operations, such as we do find at airports, with a few skilled mechanics involved in pre- and post-flight operations, and a flight operations control center staffed with a few people, two of which are the flight managers, and the third person accountable for handling all the ground operations. Flight managers, again, perform the same task whether they are in the Flight Ops Control Center or if they happen to be on board the Delta Clipper for those flights that may require human presence on board, such as for supporting missions, payloads, or for comforting the passengers that may be flying on board so they don't feel they're completely abandoned by the flight crew. To get there, we start out again from our aircraft side with lots of design margin for operation. Again, a philosophy called reliability-centered maintenance that says from the very start of the design process, maintenance is an integral part of your design criteria. And with that allows us to get into an operation flow very similar to what we have for commercial aircraft as well as our highly efficient military aircraft, and with that drive costs down. Safety is a different lesson than we fly in our expendable launch systems with our Delta rocket. There, you're always designing for the perfect one-way trip. Here, the philosophy comes in again from the aircraft that you always need to design to be able to gracefully accommodate failures and always successfully return the vehicle along with the crew, passengers, and cargo back to your spaceport. With this philosophy, then, you get into a few licensed mechanics that do all of your maintenance, and key in that is being able to dramatically drive down the operations costs. With this, then, you're really creating a truck that happens to go to space and greatly expanding the uses of space then with the low-cost routine access. The things that we do today in terms of putting satellites in orbit will expand that to being able to routinely retrieve as well as maintaining satellite constellations. We can talk about sortie trips as we now do with aircraft. For example, Ted Turner, CNN, would love to have one of these for instant coverage around the world. A space station and lots of other space laboratories get into place, into being. Then you'll want to have routine servicing for logistics, taking passengers to and from space station, as well as hauling scientific experiments up and back, and mundane things like getting rid of trash. And was mentioned, the last speaker, in terms of the low Earth operation, really explosion that's going to be taking place in terms of constituting those satellites and then maintaining them, repairing them, and keeping them up on a routine basis. The capability to do that is really available with based on the technology that's here. You've heard some of that discussed already. Indeed, a cross-section of the industry, government, labs, DOD, NASA, all conclude that what we have today on the shelf is adequate to move ahead. What's needed is a lot of dedicated hard-nosed engineering to bring that into place, and engineering from the standpoint of both the operations as well as the performance side of the equation to bring that all into being. And we're looking at pursuing that through an integrated sets of technology demonstration programs combined with flight programs and ground demonstration programs that will validate the technology as it is applied to design these totally reusable systems. So this is the incremental steps we've been following towards an operational system, which we believe can be available around shortly after the turn of the century. Step one, which we're be completing this summer in our flight test, has been the DCX or the DCX-1, and heavy emphasis there has been on validating the whole concepts of operations and consequently operational cost achievability, as well as the flight characteristics and operations that are, some of which are unique to the vertical takeoff and vertical landing system. Successfully completing that, the next step would be to move on to the next increment of demonstration and really removing the last engineering and manufacturing uncertainties with respect to achievability of the fast fraction that you need for achieving single stage to orbit with a vehicle and an airframe that can be routinely serviced, and an airframe and propulsion system that will last, in the case of the airframe, you'd like that for at least a 20-year lifetime. In the case of the engines, you'd like to get at least a couple hundred flights out of it before you send it back for a routine overhaul. Based on the results of step two, which should be no longer than a 3-year program, you'd be ready to move on and commit to full-scale hardware for the prototype of the orbital system, an orbital capable vehicle, bringing on the new engine developments that you would want for that larger scale system, and having that flying to orbit by around the year 2000, 2001, and then going on from there through a certification process to a fleet of initial vehicles around the 2002 time period. So that's kind of the process we're following and the vision of where we want to get to by the turn of the century. To do that, this then has been the major thrust of the SSR-2 single-stage rocket technology program to go from a set of visions to bringing that in terms of hardware reality. And so you know, no other way to do that than to get real hardware flying in the field with real operational experience. So that was the primary focus, and has been the focus of the initial step one, has been to demonstrate the whole concept of operation, demonstrate the capability to design a vehicle, an all-cryogenic system for routine support with totally autonomous control, and one that can operate in the same type of weather that we designed for our commercial aircraft today. Getting into a very rapid turnaround system, 7 days has been the goal. We believe that 3 days is what we'll demonstrate in a rapid turnaround test this summer. Part of that is also demonstrating that it is still possible to get through a very rapid prototyping of hardware and combine integrated government industry product teams within short schedules and short budgets to produce the flying demonstrators, and using that same process to carry on a very cost-effective, full-scale development program. The system that's been demonstrated has been a total system because a key element of it was demonstrating the whole operations. And this picture, is, I tell people, shows up the same whether it's black and white or colored. That is a colored photograph of our operations out at White Sands. Some of you have been out there can appreciate the gypsum that's surrounding our two concrete pads from which all of our operation is conducted. So what we've developed and are demonstrating is really a mini spaceport at the Clipper site at the White Sands missile range, and incorporating in all of the same operational functions that you would have for the full-scale system, and thereby using that to also validate our concept of operations, as well as the flight performance of the vehicle as it flies. Our first flight testing occurred 24 months after the contract startup, and actually about 18 months after the contract money started to flow in late in 1991. So the first series of tests that we completed under the contract were to demonstrate the takeoff, hover flight, and the ability to do the vertical landing. Some of you may know that we hoped on our first test to do that in the early column of day and kind of maximize flying conditions. As it turned out, we had one of those violent thunderstorms through there the night before. When the crew came out at 3:30 in the morning to look at the site, the trenches were full of water. So the first thing we had to do was bail out the site and decide if we could fly that day, which we decided we could, and that was late in the afternoon when the winds were up and blowing. So the first flight also began to demonstrate the ability to take off and land in the presence of winds and gusts. We had over 20 knot gusts that were present during the takeoff and landing, and soon found out that was well within our operational capabilities. We had some other fun later on the third flight, which also stressed our automated guidance system. Gives you an idea, again, some of you I know have been there, but this gives you an idea of what the simplicity of the flight stand is, and is made to, again, minimize total people involvement as well as total facility investment involvement. And the vehicle does sit on just 4 posts, no tie down prior to flight, and just 4 flame deflectors that direct the exhaust gas out parallel to the ground at takeoff. And that's worked very successfully, and in fact the deflector pads we use here are the same as what we use on our Delta vehicle as it launches from the site at KSC or at Vandenberg. On landing, again, this is a touchdown. Shortly after touchdown, the ground crew is out getting ready to attach. the purge gases and ground lines. The vehicle does set down and on a touchdown note through through sensors on the fore landing gear, shuts the vehicle down, vents the tanks, and generally gets itself ready for the ground crew to do its operation. As I said, the ground crew comes out, completes the discharge of any residual fuel in the tank, and prepares it to through just an initial walk-around inspection of the base of the vehicle, through inspection hatches, visual gauges you have as well at the site, assesses the post-flight condition of the vehicle. The ground crew then attaches what we call our U-Haul trailer, a similar trailer, the same one that we use at the rollout to haul the vehicle back over to the flight stand and prepare it for the next flight. Our flight operations control center really consists of the one van that from which all the flight operations, pre and post flight, are controlled, and then supporting the entry lanes. From the operations side, then we've pretty well proven out what we set out to do is that we can get this into an aircraft type of operations. Our cartoon of the 3 people operating it has been turned into reality with the 2 flight managers, Pete Conrad, who's the flight manager, Tom Ingersoll is deputy, and Jerry back there on the drums, or he's carrying out all of the ground operations, Jerry Coleman. The maintenance of the vehicle is all on-vehicle maintenance, large access panels available for the ground crew to do inspection, servicing, as well as being able to get into the propulsion bay area for inspection and servicing. So in terms of demonstration, when we were at the NASA White Sands test facility and doing static testing, we were able to get in 2 complete hot firings in 1 day. That would be equivalent really to an 8-hour turnaround time between flights. Out on the range, we were doing 11 days, and I said we'll demonstrate this summer a 3-day turnaround capability. Operations crew, as I said, is really the 3 people in the Flight Operations Control Center, and supported by 7 hands-on mechanics for maintaining the vehicle and all the ground systems. We've had a total of 15 people that constitute our total operations crew, including our secretary, which really keeps all the operations running down there. What we're doing is really validating the operations cost models that we use, because the numbers of people, tasks, jobs, assignments for these people were derived from the model that we use for determining the cost and operations for the full-scale vehicle. So in the same way that, for example, our computational fluid dynamics people were validating flight codes on say the base drag of the vehicle, our operations people then were validating the overall operations code, and consequently the cost codes. The flight operations, again, we modeled that after the flight screens from the MD-11. Again, going into a lot in terms of human factors and displays. This typically shows what Pete Conrad may monitor during pre-flight operations. If he gets a caution light that comes up on a particular subsystem, he can call that up, understand what the nature of the problem is, decide whether to fly with it or send a mechanic out to service it. Similarly, Jerry Coleman, as he looks at the ground operations, has a screen that he goes to, and this is all on silicon graphics display with a mouse, so we can, when he wants to start a load operation for helium, for example, he can click on that and then watch as the system goes through its automated helium pressurization report back in on the status that it's ready to go. And then he turns that information back over to Pete Conrad, who can make the decision then to go ahead and fly the vehicle. When he presses the start button, then the vehicle goes into an automated start mode, bringing the engines up to a 30% idle mode, so you can do an all systems check. And then once it's verified itself, it's ready to go. It throttles up to takeoff power and literally flies on the stand, completes its mission, and then shuts itself down. The data we're getting out of the system, it is validating our pre-test predictions that were done about a year prior to the flight test. And so we're collecting real-time data here on the operations side in the same way that we are on the performance side. With this is really fitting our operations model. Again, we've used aircraft operations as kind of our chinning bar, say how well are we doing, and this shows a similarity in terms of percentage breakdown of where we are versus the aircraft model. Also shows us areas that we need to concentrate on, improve to even drop our operations costs lower. Where do we believe we can get in terms of operations cost in this plot of dollars per pound of low Earth orbit or dollars per flight, which we like to use, I think is maybe even a more significant parameter. You want to get down to the lower left-hand corner. And, first obvious thing is that if you don't throw the vehicle away, you can drop the cost, about 70% of the cost right from the start. Then you got to work hard to really keep the overall operations cost, a small crew, efficiency in terms of the amount of propellant that you use. Your vehicle needs to have good maintainability or high reliability so that the numbers of replacements per flight are kept to a minimum. With that, we believe cost per flight down below $10 million per flight are not only feasible, they're quite reasonable to achieve. And then our goal then is to keep dropping those down, because as we want to get into, as most everybody in this room, I certainly want to be able to afford to fly this, you're going to need to get down in terms of cost per flight that are approaching $1 million per flight or less. Again, quite achievable things to do. And that'll come with more operational experience as well as more flights. On some of the key technologies, putting together, well, again, was one of total integration of the system, the ground and flight system, getting into a total autonomous flight operations. This is uses a GPS updated INS system, so we're already demonstrating redundancy, for example, in landing capability with the onboard landing radar system, the INS system, as well as the ability to use a differential GPS system. The takeoff and landing environments I talked a little bit about earlier, particular concern to us in terms of removing design uncertainties was the effect that we're going to run into as we landed the vehicle. You get fountaining effects as the plume hits the flat concrete pad and comes back up on the base of the body as well as the side, where they're going to create forces that our flight control system basically wouldn't be able to predict. We did a lot of wind tunnel testing, as well as CFD calculations, and in the end, like all flight systems, you have to get out, fly the real environment, and see how well you do. And fortunately, in this case, we found that the environment was somewhat more benign than our tunnel testing and model testing would have predicted. And we were able to not only handle the effects of the plume effects during landing, but also the wind and gust effects during flight. The propulsion, again, most all of our control has been done with just thrust vectoring control of the rocket engines. One of the advantages of landing vertically is, by definition, you're a powered lander. And one of the things that our aerodynamicists have really grown to appreciate is the fact that rocket engines give you a lot of control horsepower at 0 Q. And so you're able to handle maneuver in the winds and the disturbances with great agility. Also, the basic avionics system then that we're putting together is one that pretty well is the same architecture as we'll be using throughout the development on into the operational system. So we have a good leg up in terms of developing the not only the basic architecture but the software that goes along with it. In terms of some of the performances to date, we're wondering how accurate our system was going to be in landing. We had to at least land on our concrete pad. We didn't want to land in the desert. Our uncertainty going in was we might have an uncertainty circle of some 20 to 40 feet. And actually, we set down within about one pace of during each of the 3 flight tests. And that amounts to about 1 bit error in the INS system. Horizontal landing velocities, even though you're landing vertically, if you have large horizontal components on your touchdown velocity, you'll tend to drag on the skids, and that puts additional loads into your vehicle that you have to take out, which amounts to more weight. And so less horizontal velocities are better. Again, we came in at least an order of magnitude less than what's required. The same way on vertical velocities, you'd like a nice soft touchdown, which we were able to achieve. And one that is approximate a 4-point landing. One thing you don't want to do is put a lot of tip angle into it, for the fear that if you tip, you might just keep going before you shut your engine off. And again, that has not been a problem. To date, we have completed the initial tests that we set out to do under our basic contract. We'd actually anticipated getting 2 flights completed and did get through 3. And got into proving out a lot of the flight control concepts, checking out some of the aerodynamics, and both the landing, takeoff environment, and then with all of these, the maintainability, the turnaround capability. Under this contract extension, which is now underway, we'll continue to expand the flight envelope, finally ending up at an altitude of around 8,000 to 9,000 feet, where we'll demonstrate and work through the rotation maneuver that we go through as we go from a nose forward flyback position to a base first landing position that we'll use as the vehicle returns from space. Again, a page out of our aircraft heritage is one of going at this in terms of a flight envelope expansion. You're moving into areas for which there is no database, and you're extrapolating information that you derive from static tests and calculations. And so this gives a process then for the engineers to learn as you go along. And so you can always comfortably fly within the range of what you think is a good boundary on your next flight projection. This is also a key element in terms of being able to reduce the development costs of reusable vehicles versus expendables. Because when you stop and think about an expendable, each time you do a flight test, you lose the vehicle and the consequent costs along with it. Whereas a reusable system, you can continually use this process of the flight envelope expansion. You get your vehicle back each time, and you make improvements on it. And again, just like an aircraft system, you learn as you go, and you also increase the reliability as well. Another area, I think as we mentioned, was again, demonstration of the ability of a integrated government product teams to carry out programs in a very rapid prototyping style. And we've been very successful in doing that with the BMDO program office. And they've become somewhat the model now within the Air Force and DoD as the style to emulate. And it really is one where you enter into a partnership with the program office in terms of carrying out in a very rapid manner, in this case, the development of the experimental vehicles, but one that can also carry on the development. The advantages are twofold. One is a significant reduction in overall cost for accomplishing that. And then along with that, and as a part of the cost reduction, is the fact that those rapid prototyping processes will take less time, and you get to a product sooner, you get to experimental results sooner, allows you to get on into the next step sooner. And again, as I said, a key element of that has been the government side, and Major Jess Vonnevold, who's our program manager at the BMDO, has been a real leader in that process, and one that now that two partners at NASA are picking up on, and one that he'll carry on into the Air Force. Within that process, again, we came in with the international team that delivered these individual parts, sub-assemblies. This is kind of showing how they came into us in about the November-December time period of 1992. And from that time period, we were able then to very rapidly assemble those systems such that by the February time period of 93, we had all the basic core vehicles assembled and electronically checked out. By March, we were putting on the outer aero shell and the landing gear. By late March, we were into doing static checks. We had our first liftoff with courtesy of a crane in the hangar. Verify our radar systems, validate signals, and sign correctness in our flight control system, and we discovered we had a sign reversal in the software, which was quickly taken care of. From there, in March, we had a rollout at Huntington Beach in April. By May, we were set up in operating at the White Sands test facility operated by NASA, where we carried out about 11 static firings and tests, and including this at a couple of days of getting 2 complete vehicle system checkouts and runs within a single day. An unsung hero in all of this, and part of what made it all possible, was the very rapid prototyping development we used for the software. In fact, as I told Matt Maris, who heads our software development, if it could make the whole vehicle out of software, I would, because it performed so miraculously. First program I've ever had where software came in ahead of schedule and they gave budget back. The thing that it did for us, the thing that it also did for us is provided a complete set of software that was available from the time that we were going into assembly. And so the software was there actually assisting in the whole integration and checkout of the system. The rapid prototyping of the software also allowed the flight control engineers to act very interactively with the software development. So it wasn't a case where, the software development people wanted their notebooks and therefore all the inputs in at least 9 months in advance of writing software, and you had to freeze your final solutions for your flight control system. And they could work right up within days of the time of the software development and have those most recent changes incorporated. The other key element of that is, again, one on the operations side, because we'll use this same process and have used that same process in developing our mission software. where, for example, in our testing at White Sands, we could load in, develop, and load in the new flight profiles for each test day, including a total hardware of the loop sim validation within a 24-hour time period. Again, that's represents a tremendous cost savings over how business is done today. So with the summer's flight tests, we will complete really the step 1 of the validation and begin moving into step 2. We'll have an intermediate step in here, a precursor step, of one that we're beginning to take on with NASA in terms of beginning to validate the applications of some of the advanced lightweight systems. Saw a little picture of this earlier. This is representative of the lightweight composite cryogenic tanks that we've developed and tested, and we'll be reconfiguring the DCX for NASA into the DCXA. And under that program, then, we'll be validating the capabilities of the lightweight tanks, new oxygen, new hydrogen tanks, some new propulsion and structural components, the ability of those to really perform and be maintained in a real operational environment, and get us well on the road to that next step of validating the capability that you and I all want to get to. Is where we've got spaceports around the world we can travel to, and like all my friends in Japan, they'll have the capability of, if they get up in the morning and want to attend a business meeting in LA the night before, go ahead. I get back in time for dinner.
Drop in.
So with that, we're going to look at another shrinking world. Eventually, we'll be looking at international route maps. Again, in addition to this being very rapid, low-cost transportation to space, it's also very rapid, low-cost transportation to any place in the world. And talking to my friends who came here from Australia, they would appreciate getting here into Toronto. Would be a 2-hour ride versus sitting on the airplane for a day. As we get through this, we'll have really completed the vision that we maintain. We're really being able to open space, the spaceways that you and I can travel on, as well as commerce, to really open the whole economic potential for space, as well as for science and exploration. The only way you get there is flying hardware. Showing view graphs is a lot of fun, and you never make many mistakes with view graphs. Until you get the hardware out in the field and learn from it, is really the way that you accomplish the vision. And we're looking forward now to moving on to that next step. Thank you. I want to make a commercial. We've had a very exciting program going in terms of education, and I would encourage those of you who are interested in participating to contact me. But it's a real hands-on learning program where we're interested in getting real-life projects, if you will, out into the classroom, and working this either at a classroom level. In this case, as we've done at Claremont College, which is close by, and what you see here is the work that students in the psychology department put together in terms of a design for a passenger cabin, probably first class, as you might go to spend a couple of days tour in space. They did that last year. This year they completed a similar design, but for the point-to-point transportation with a 50-person, again, business class accommodation for they traveling any place in the world. What we do and offer is is a resource and act as a technical evaluators and can participate as much or little. And the little may just be giving suggestions for what interesting class projects, individual projects might be. For example, we worked with Texas A&M this past year in terms of a senior project where they had 150 people participating in integrated product teams and actually went through a complete design of a Delta Clipper. And we went down for the kickoff and midterm and final reviews. And again, it can be from the technology side, performance side, to the operations side. I'm interested in finding somebody that's interested in writing or poetry. Part of what I think we need to do is, again, particularly in talking to the aerospace companies, is get out of our own little communities where we have always been comfortable in talking to ourselves, advertising to ourselves, and reaching out and getting the greater public interested and involved and realizing that they too have a destiny in space. And a commercial. Thank you. Yes, sir.
Can I ask you when you plan on actually starting to fly it again this summer, DCX, and when you hope to wrap up the DCX program?
The question was when we plan to start flying the DCX this summer and how long do we wrap up. Our full crew is down there now. We plan to have what we call a burp test, first static test on the stand around the 3rd, the 6th of June. And then our first flight is scheduled now for the 11th of June. And then later in the month, we'll go into our rapid turnaround 3-day flight test. And then in early to mid-July, work on up and do the rotation maneuvers. And so we should be pretty well wrapped up by the end of July. Yes, sir.
Three-part question. The first part's really easy. In the test so far, have you tried shutting down and reigniting the engines in flight? Second part is when you move from the prototype to the full-scale version, what are the scaling factors involved? And when I say scaling factors, I mean not just the physical scaling factors, but other scaling factors in terms of ground support, complexity of the control systems, and so on. And the third part of the question is the way you're doing this project teaching any lessons to the government in terms of how it wants to do business?
So the first one dealt with the engine shutdown. We've not had to do that. We do have built in the flight control system an engine out capability, such that if we do lose one of the 3 engines, we can compensate and land safely.
But when you go in orbital mode, you definitely...
In the orbital mode, we do have total engine out capability every time for the time we leave the flight stand, time we return. Returning and setting down, probably want to use half of the total number of engines we have for landing, so you do have a lot of redundancy. So we do have that programmed in, and if we have time in the upcoming series of tests, we probably won't do a total engine shutdown. We may significantly throttle down one engine just to validate the onboard sensors to pick up and realize you're losing thrust over in that part and readjust the other engines. The second question dealt with scalability as we're going from where we are now to full scale. And some of it is directly scalable, what we've done now in terms of the basic aerodynamics and control. Software algorithm developments are, again, all pretty well scalable. You put in different factors as representative of the larger physical scale of the vehicle. And the same goes for the operations side. We have a vehicle that's 3 times as large, more propellant, larger stands and facilities to handle it. but the basic processes and so on would be the same. And the scaling would be by size and by additional number of components, for example, that you need to maintain and check out.
Do you expect that 3 operators would be enough for suborbital flights?
Yeah, actually, Pete wants to get down to a 2-person cockpit, and we could do that. And but the basic ground systems and the way we operate and handling is homegrown from what we have now. What you will see in addition, either in the flight control center or in the adjunct center, will be whatever mission operations or payload that might be unique for a particular flight might be carrying on.
What is the physical scale factor between the current prototype and the orbital version?
We're at about a 1/3 scale of what we think the full-scale operational system would be. The last question dealt with the kind of a model and of the way of doing business and how's that being received within the government. And very, very favorably. We've all heard a lot of talk and discussions on the whole business of reinventing government. Those of you who've had the privilege of hearing some of Dan Golden's very inspirational talks know that he, as the administrator, is dedicated to reinventing NASA and returning it to the days when they are the centers of technical excellence and can offload some of the other duties that have been imposed on them. And part of that is being able to do, and you've all heard the phrase of cheaper, better, faster. And that's kind of what this is all about. But being able to do that without sacrificing quality as you go through it. And the fundamental process we're using is no mystery. It's called integrated product teams, and that just says it's a process that allows the people that need to be involved making the decisions, that they have the authority as well as the responsibility to do that, and also that all the people that are affected by those decisions play a part in it. And so it's a way of affecting communications, both within industry partners, and within industry partnership with the government. And I'm here to tell you it works, and works just fine. And, it's a model that the folks at NASA Marshall have adopted. For the DCXA team, the government office there consists of 3 people, and they intend to keep it that way, and have been really setting on a very, very fast pace that we've got to hurry along to keep up with. So very, very positive, and I would bring that as a positive message to this group that things are changing, and that's one of the major changes that's happened since last year. Yes, sir.
Could you give us an update on the funding situation?
That's less rapid prototyping. Question? The question dealt with the funding situation. The good news is that we're back in the air with the additional funding we needed to do our expanded testing, and so that's in place. There are ongoing discussions now with respect to the $35 billion that remains within the DoD budget that was appropriated last year for fiscal '94 to kind of continue this process through a competitive RFP for the next follow-on step 2, as I illustrated. Within NASA, NASA's taken a very aggressive lead. Again, this has been the leadership of Mr. Golden in stepping up to the single-staged orbit, a result that came out of NASA's last year Access to Space study. They certainly embraced that as their next launch system, and they've gone forward with funding in '94 to start the program, and funding requests in Congress now for '95 and '96, and I think are being very well received there, and supported by Chairman Brown, for example. specifically in the line item for SSTO. So it's, as usual, Washington's a bit murky, but it is also, I think, a very, very positive trend where we've come in this past year. So, and again, thanks to all of you in this room too, who have been very, very proactive in getting the word out in your communities, and that word again gets into Washington. And as Washington understands what their constituents want, things do change. It's not going to be overnight, but it is the trend is right. Yes?
Yeah, how does the current set of tests that you're going to run compare to the original? Have you basically just restarted where you left off, or have you changed around the scheduled tests?
Our plan, the question was how do our extended flight testing compare with what we originally had planned if the funding had been immediately in place in October. We basically planned to move on from where we were at the completion of testing last year. We're going to go through a lot of checkouts and validations and through static testing prior to committing. But everything we're seeing so far in terms of checkout, condition of equipment is very, very encouraging. And so I think we'll be able to proceed on into the flight envelope expansion with some confidence. Yes, sir.
Is the Department of Commerce engaged in supporting this program?
Department of Commerce, I think, is getting more involved. And they, for example, one of the great things that was done in the Mormon Review Committee that acted for DOD was that, again, in their process, instead of just looking within DOD individually for requirements, they broadened that to include NASA and then also the Department of Defense, Department of Commerce. So they were active participants in the development of the Mormon recommendations. They've also been active participants in the Office of Science and Technology Policy in developing the country's new launch policies, which should be out within a few weeks. So they are becoming a more active player, along with the Department of Transportation. Again, as I mentioned to some of you in the talk yesterday, I think if we're going to normalize space and open it up more, we need to get more of the agencies that have been traditionally involved in carrying out these functions for land, sea, and air involved in the space functions, and make it a less unique quantity and one that we can use existing institutes, processes, and policies to help further implement.
Isn't the OSTP study recommending that NASA take the solstice to orbit technology and study it until 1997 for a decision? Instead of building anything, aren't they being encouraged to study it only? And how do you feel about that? Is that a correct statement?
I have not seen a final draft of it. There have been various wordings, and then, like all documents, you know, the spin doctors put their own benefits on it. Let's see, what is clear, I think, and it also came out of the Mormon study, was a realization that we need focus within this country, and so give the focus for the reusable systems to NASA, for the expendable systems to DOD, and then also with through cooperative programs, each of those agencies would support the other in their particular lead and support roles. The 1997 date is a bit of a mystery and exactly what that means. I don't think it precludes doing aggressive testing. And for example, the DCXA is going to be over and done with before 1997. But I think the general concern in Washington and all of us U.S. taxpayers know is the budget, keeping that under control, and dealing with other issues that we have ongoing of healthcare and other demands for budget, and balancing out within that a program that really starts us down a new direction in space. And if you stop and think about where we've been for the last 30 years in space, has been largely driven by exigencies of the Cold War. As a result, we have an infrastructure in place that supports the Cold War, but not really public space involvement. And so more than anything, that's what we need to do is to work on access to space and our whole space systems as a very fundamental infrastructure problem to be dealt with, certainly in the United States as well as other countries. Once the basic transportation infrastructure is in place, then watch the entrepreneurs take over. 6 o'clock, time for dinner. Thank you.